Hey everyone, in this video we're going to learn how to solve compound linear inequalities, and we're going to start with a definition. A compound inequality contains at least two inequalities that are separated by either and or. A few examples: x is less than 1 or x is greater than or equal to 5, x is less than or equal to 4 and x is greater than 1, -2 is less than x less than 10. The last one looks like it doesn't belong. In the definition, we said inequalities that are separated by either and or. Clearly, first two examples fall into that category. The last one, not so much. But if we think about it, this would be -2 is less than x, and x is less than 10, if we read it separately. So let's write that out separately. So -2 is less than x, and x is less than 10. If I want to make it look like this one, I could say x is greater than -2. I can switch this inequality around, and x is less than 10. So although it may not look like it falls into this definition, it does in fact do so. Now the question is, how do we come up with the solution sets of these compound linear inequalities? Right? How does their solution set look when we go to graph it on the real number line? And that's what we're going to figure out next. The graph of a compound inequality with an end represents where the graphs of the inequalities intersect. A number is a solution to the compound inequality if the number makes both inequalities true. So we're looking for values that make both inequalities true. Has to be both. So state three numbers that satisfy the following compound inequality. X is less than or equal to 4, and x is greater than 1. So we need numbers that are less than or equal to 4 and greater than 1. So 2 is an example, 3 is an example, 4 is an example. We could even said 2.5, 3.5, but any number that's greater than 1 and less than or equal to 4 would fall into the solution set of this compound inequality. Now, graph this solution set on a number line. So we have our number line. So we have 1 and we have 4. For compound inequalities, what I like to do is above the number line, I like to graph each solution set separately and then figure out how that's going to transfer down onto the number line. I'm going to do it with a highlighter to help exemplify what we're looking for. So x is less than or equal to 4. So we're going to put a close point at 4, and we're going to shade to the left. And then I'm going to take the blue highlighter. X is greater than 1. So I go open point at 1, and we shade to the right. Now we're looking for the intersection of the two solution sets. Now the nice part about doing it with highlighter is we're looking for where it turns green. That's the intersection, right? That's where both inequalities are true. So if we look, it's green right in here. So we're going to start with an open circle at 1, a closed point at 4, and the only place that it is green is right in between those values, in between 1 and 4. Okay, so that's our solution set to this compound inequality, right? We looked for the intersection right here of those two inequalities. Now, how else could we represent this compound inequality? Well, this gets back to that first slide. Instead of connecting it with an end, can I rewrite this inequality as just a sequence of inequalities? So we can say that 1 is less than x, which is less than or equal to 4. That would be equivalent to x is less than or equal to 4 and x is greater than 1. Okay, so if you're asked to write a compound inequality, you can use either this or this. The graph of a compound inequality with an OR represents the union of the graphs of the inequalities. So union means we're going to join them together. A number is a solution to the compound inequality if the number makes at least one of the inequalities true. Now, this is a key difference. It only has to make one of the inequalities true. As long as that's the case, it's part of the solution set. Whereas with an AND compound inequality, the values have to make both true. So that's a really important piece to pick up. So state three numbers that satisfy the following compound inequality. X is less than 1 or x is greater than or equal to 5. So let's first pick a value that's less than 1. So 0, that's a solution, right? Makes this inequality true, does not make this inequality true. Now let's look at the other inequality. So if we pick 6, that's a solution to this inequality, not the first. But again, all we have to do is make one of the inequalities true. And now we could pick from either one. So let's say we go back to the first one, let's say -3. Right? So there's plenty of numbers we could choose. These are 3 of them that would make this compound inequality true. So graph this solution set on a number line. So we have 1 and we have 5. I'll do the same thing with the highlighters. So I'll start with yellow. X is less than 1. So open circle. That's not an open circle. So open circle. Shade to the left. And then we'll go blue. X is greater than or equal to 5. So close point. Shade to the right. Now when it was an AND, we were looking for where these highlighters turned green. But now it's an OR. So we're just joining all of our solution sets together. So basically anything we've drawn above the number line is going to be put on it. So our solution set is going to look like this. There is the graph. So an OR, whatever we have above, goes on our number line. And we're looking for the intersection. We're looking for that change in color. So write a compound inequality to represent each solution set. So this inequality, that would be x is less than or equal to -1. This inequality, x is greater than 2. And we have to figure out, do we connect them with an AND or an OR? Well, if we think about this logically, any value in this inequality can't make this inequality true, and any value that makes this inequality true can't make that inequality true. So we can only make one true at a time. Well, let's think about it. Only one inequality can be true at a time. That's got to be an OR. In the second example, we have -2 all the way to 5. So we have x is greater than -2. And then in the other direction, we have x is less than or equal to 5. And all of these values in between make both of these inequalities true. So since the values make both inequalities true, we would write that as an AND. Now there's one other way we can write this inequality. We could also write -2 is less than x, which is less than or equal to 5. So when our compound inequality has an AND, we can write it in this condensed manner. Not true when it's an OR. An OR, this is it. We're leaving it. Nothing else we can do. An AND, typically we can rewrite it in a more compact nature. Can x not equal to 7 be considered a compound inequality? Well, let's think about the number line or the solution set here. So we'd have 7, open circle, and we'd shade in both directions. Well, let's treat this, so if we look at the left side, we'd be looking at x is less than 7. On the right side, we'd be looking at x is greater than 7. Now anything that's greater than 7 can't be less than 7. Anything less than 7 can't be greater than 7. So the way we're going to connect these two inequalities would have to be with an OR. Well, then the answer is yes. This, x is less than 7 or x is greater than 7, is another way to rewrite x cannot be equal to 7. So it's a nice connection with something we did earlier. Graph the solution sets of the following compound inequalities. So x equals 4 or x is greater than 8. Well, kind of weird because we have equals here, but I think we'll be able to handle that without an issue. So we have 4 and we have 8. So again, we'll take the highlighter. So x equals 4, so that's going to be a point right above 4, and that's it. There's no shading, only that single point is part of the solution set. And then x is greater than 8, so we have an open point and we shade to the right. Now remember, when we're dealing with an or, anything we shade above the number line is going on it. So we have the point here, and we have the inequality there. There's our solution set. Our next one, x is greater than or equal to 3, or x is less than 6. So we have 3, we have 6. So x is greater than or equal to 3. So close point, shade to the right. And then x is less than 6. We have open point, shade to the left. Now, normally when these solution sets overlap, we're looking for where they turn green. But this is an or statement, right? And or, what do we say? Everything that we draw above the number line goes on it. Now the big question is, at 6, do we have an open or a closed point? Well, the yellow fills in the open blue point, so we're just going to have this whole number line. This whole number line is going to be graphed. So this is an example where the solution set is all real numbers, right? The whole real number line is our solution set. Now the last one, x is greater than 0 and x is less than or equal to -5. So we have -5 and we have 0. So x is greater than 0, so open point, shade to the right. X is less than or equal to -5, so close point, shade to the left. It's an end compound inequality, so we're looking for where they intersect. Well, we didn't get any green. The highlighters never overlapped. No intersection. So we don't shade anything on the number line. And just so we're clear here, and we don't think that I forgot, this would have no solution. There is no value that can make both of these inequalities true at the same time. Right now, I know these are a little bit weird, okay, compared to the ones that we looked at, but I think they're important because they make us think. So we don't get in the habit of just always assuming, oh, or always looks like this, and always looks like that. No, we have to be thinkers. We have to think about the compound inequality that we're given. And if we have a strategy, it really doesn't change regardless of the problem. So now let's get to those problems. Solve each of the following compound inequalities and graph the solution set on the real number line. So first thing to do is solve both of these inequalities to their simplest forms. So we'll distribute the 4. So we have 2x minus 3 is greater than 4x minus 4. We can subtract 2x on both sides. -3 is greater than 2x minus 4. We can add 4 to both sides. 1 is greater than 2x. Divide by 2. 1/2 is greater than x. And on the right inequality, we can subtract x from both sides to start. So 5 is less than or equal to 2x minus 1. We can add 1 to both sides. 6 is less than or equal to 2x. Divide both sides by 2. 3 is less than or equal to x. And we're connecting that with an or symbol. Now, if we need to, you could rewrite these as x is greater than 1/2 and x is greater than or equal to 3. But I think it's important that we're able to graph it in either form. So now we go to our number line. So we're going to put 1/2 and 3 on the number line. Now we'll go to the highlighter. So x is greater than 1/2. x is less than. Well, good thing I caught that. I didn't switch the sign when I rewrote it. And that is one of the disadvantages of rewriting it, in case you make that mistake. So we have x is less than 1/2, so shading to the left. And then x is greater than or equal to 3. Right? So I graphed each solution set separately. We're connected with an OR, so we're going to put both of these solution sets on the number line at the same time. So there is the solution set to this particular problem. Next one. 13 minus x is greater than or equal to 4, and 4/3 times the quantity x plus 2 is greater than 8. Start with the left side. So subtract 13 from both sides. Negative x is greater than or equal to -9. Divide both sides by -1. Now remember, when we're dividing by a negative, we got to watch that inequality sign. So it's going to switch and become x is less than or equal to +9. Now on the right inequality, I'm going to start by multiplying by 3/4 instead of distributing. You can do either, but I think multiplying by 3/4 is going to make our life a little bit easier. The 8 and the 4 simplify. So we have x plus 2 is greater than 6. So just another way to think about this problem. We're going to subtract 2 from both sides. So x is greater than 4. And we're connected with end. So we'll create our number line. So we have 4 and we have 9. And we'll pull out the highlighters. So x is less than or equal to 9. So close point at 9. Shade to the left. X is greater than 4. So open point. Shade to the right. So now we're looking for the values that make both inequalities true. So that's where the highlighters turn green, which is right in this section there. I'll actually use the green marker. Now notice, not green here, so it stays an open circle at 4. It's green on the close point, so close point at 9. And then our shading, the values that make these inequalities true are right in between. And again, we can check this. Pick a value between 4 and 9, so like 7. 7 is less than or equal to 9. Good. 7 is greater than 4. Good. Check a value less than 4, like 0. 0 is less than or equal to 9. Good. 0 is not greater than 4. So anything over here, no good. And the same thing can be shown there. So we can check ourselves as well with these problems, as long as our work is correct. 4 is less than or equal to x minus 7 all divided by 2 less than or equal to 10. So the first thing we can do is multiply each inequality by 2. So we can multiply this whole thing by 2. So we'd have 8 is less than or equal to x minus 7, which is less than or equal to 20. And then we can add 7 to each part of this inequality. So we'd have 15 is less than or equal to x, which is less than or equal to 27. Now, when we don't have the and or, I think it's a little bit easier. We put 15 and 27 on our number line. And our solution set, so close point at 15, close point at 27, and the inequality, the compound inequality, illustrates where we should be shading. We shade values that are in between 15 and 27. So shade in between. Now, what we could have also done is broke this apart into a compound inequality with end. So we could have said that 4 is less than or equal to x minus 7 over 2, and x minus 7 over 2 is less than or equal to 10. That makes it look a little more familiar in comparison to the previous examples that we've done. And if this makes more sense, by all means, do this first and solve out. And then you would figure out your solution set the same way we had done in the previous 2 examples. Okay, 2 more to go. A lot of details in this video. 2x plus 7 is greater than or equal to 10 minus x. So we'll start by adding x on both sides. 3x plus 7 is greater than or equal to 10. Subtract 7 on both sides. 3x is greater than or equal to 3. Divide both sides by 3. X is greater than or equal to 1. And on the right side, we'll distribute the 6. 6x minus 12 is greater than 2x plus 8. Subtract 2x from both sides. 4x minus 12 is greater than 8. Add 12 to both sides. 4x is greater than 20. Divide both sides by 4. X is greater than 5. So we have x is greater than or equal to 1, or x is greater than 5. So we go to the number line. We have 1, we have 5. So x is greater than or equal to 1. There's that solution set. X is greater than 5. There's that solution set. And it's an or, so we're looking to put everything that we drew in highlighter on the number line. So we have a close point at 1. Now the question is, when we transfer it down, is the 5 an open point or a closed point? Well, the yellow highlighter goes right through that open point, so the yellow would go down onto the number line. So that's actually going to make this a closed point at 5. Now you don't have to make it a closed point, you can just shade to the right. But just so we illustrate that a little bit more clearly, that yellow part of the solution set inside that open point comes down and makes it a closed point on the number line. So really, the solution of this compound inequality is just x is greater than or equal to 1, which, think logically. Again, I want you to think in this lesson. If a value is greater than or equal to 1, then this statement is true. Then we don't really care about this statement in this case, right? Look at how we drew it. Only one of the inequalities has to be true in an or statement. So at 5 makes this inequality true. It doesn't make this inequality true, but that's okay. Only one has to be true, so 5 would be included. Again, think if you're not sure, take that value of 5. If you're not sure if it's open or closed, plug it into the inequalities. See if it makes, for an or statement, see if it makes one of them true. Last example, 5 minus x is greater than 7, and 5x is less than 3 times the quantity x minus 3 plus 1. So we'll start here, subtract 5 on both sides, so negative x is greater than 2. Divide by negative 1 on both sides, x is, when we divide by a negative, make sure we pay attention to that inequality, x is less than negative 2. And on the right side, we'll distribute the 3, so 5x is less than 3x minus 9 plus 1. 5x is less than 3x minus 8. Subtract 2x on both sides. 3x is less than negative 8. X is less than, divide by 3 on both sides. More space there. X is less than negative 8 thirds. Okay, so we have x is less than negative 2, and x is less than negative 8 thirds. Okay, so we go to the number line. So negative 8 thirds is about negative 3, so we have negative 2, and we have negative 8 thirds. So x is less than negative 2, so open point, shade to the left. X is less than negative 8 thirds, so open point, shade to the left. Now we're looking, it's an and statement, so both inequalities have to be true. So we're looking for our highlighter to have changed colors, to turn green. Well, it only turned green in this section here. So going to have an open point at negative 8 thirds, and we're going to shade to the left. Right, only that section where it turned green is going to come down onto the number line. So we covered a lot. The compound inequalities definitely take a step up. We saw some weird looking solution sets, but again, we got them all the same way. Graph the two solution sets of your smaller inequalities separately. I choose to do it above the number line. And then we have to ask ourselves, are we only looking for one of these inequalities to be true? Is it an or statement? Well, then everything that we shaded is going to come onto the number line. Or is it an and statement and both have to be true? Well, then we're looking for where the inequalities, the solution sets, intersected. And when I used a highlighter, that meant we were looking for that green color. So, rewatch any parts that you were unsure about. Really important to pay attention to those details. And the only way you're going to get better with this is practice.